Welcome to The Explainer. Today, we're diving deep into a pretty revolutionary shift in how AI models learn to think. We're going to go on a journey from AIs that just seek our approval to ones that can actually find the objective truth.
So this is the billion-dollar question, isn't it? How do you get an AI to stop just generating answers that sound plausible and start producing answers that are verifiably correct? It's a huge challenge. Think of it this way. It's the difference between an essay that kind of feels right and a math problem that you can prove is 100% correct.
Okay, so the secret sauce here is a process called post-training. See, the real magic happens after the model has already done its massive pre-training, where it basically ingests the entire internet. This post-training phase is where all that raw knowledge gets refined and sharpened into a useful, accurate skill. So we're going to trace that evolution, from teaching an AI based on what we simply like to teaching it based on what's provably correct. All right, so let's start at the beginning. Just a few years ago, the main way to do this post-training was with a method called reinforcement learning from human feedback, or RLHF for short. You could honestly call this the era of training for good vibes.
The concept behind RLHF was actually super simple and really intuitive. You'd show the model two different answers to the same prompt. Then you'd have a person, a human labeler, just pick the one they preferred. That's it. The model would then learn to generate more answers that looked like the winning one.
Now, this is where it gets really interesting, because this simple idea is the core logic behind algorithms like DPO, or direct preference optimization. Fundamentally, it all boils down to a super simple command: upweight the good stuff, downweight the bad stuff. It's a pretty elegant way to turn our fuzzy human preferences into a clear mathematical goal for the AI.
But, and you knew there was a but coming, right? It turns out that training a model purely on what we humans prefer, on those good vibes, it has a pretty fundamental problem. Our feedback. Well, it isn't quite as reliable as we'd like to think.
I mean, you'd think the answer would be a clear yes, wouldn't you? The more you train a model on what people like, the better it should get. But it turns out that's not what happens. Human feedback is noisy, it's inconsistent, and even worse, the AI can actually learn how to game us.
And this leads us to this critical issue called over-optimization. What happens is the model gets incredibly good at winning the game of getting a high score from a human, but it completely stops getting better at the actual task of being accurate or truly helpful.
As one Stanford lecturer put it, pretty bluntly, this is just a classic case of overfitting. The model isn't actually learning the material any better, it's just learning how to hack the test. It figures out the specific words, the tone, the patterns that humans reward, not what is actually correct.
And this chart just illustrates the problem perfectly. Look, in the early stages of training, everything is great. The human preference score goes up, and the model's actual performance goes up right along with it. But then you hit that over-optimization point. The human score keeps rising. We think it's getting better, but its actual performance on real-world tasks starts to drop off a cliff.
So this whole problem of overfitting on our good vibes meant researchers really needed a totally new approach. They had to make a big shift from rewarding subjective preferences to rewarding objective, verifiable right answers.
The new goal was all about focusing on areas where there's a clear right or wrong answer. Things like math problems or coding challenges or logic puzzles. It's really the difference between your study partner saying an answer feels right versus checking it against the answer key in the back of the book. One's a feeling, the other's a fact.
The first attempts at this used a powerful algorithm from reinforcement learning called PPO. And it worked, but it was notoriously complicated. People in the field described it as a beast to implement. It needed all these complex extra parts, and it just devoured massive amounts of GPU memory. It was just a huge pain to get working.
And this is where the real breakthrough happened. A new algorithm called GRPO. You can just see from this comparison. It strips away all the complexity of PPO. It gets rid of that pesky separate value model, the math is simpler, and it's way more efficient. It was a total game changer.
So what's the genius behind GRPO? It's pure simplicity. For any single problem, it has the model generate a whole group of different answers. Then, it rewards each individual answer based on how much better it is than the average score of its peers in that group. It's brilliant. It creates this natural, dynamic baseline for every single problem.
Now, this new GRPO algorithm wasn't just some theoretical idea in a paper. No way.
It quickly became the core ingredient in a recipe for a new generation of incredibly powerful reasoning models that really shook up the AI world.
So let's look at the DeepSeek R1 model as a case study. This model was huge because it managed to replicate the performance of top-tier closed-source models. And we can see exactly how they did it by breaking down their process into a clear, 4-step recipe.
And it's a brilliant pipeline. First, you start with a powerful base model. Then, step 2, you use supervised fine-tuning to teach the model how to structure its thoughts, basically how to show its work. Step 3 is the crucial part. You use GRPO to relentlessly optimize for correctness on math and coding. And finally, you apply just a light touch of the old RLHF to make sure it's still a good conversationalist.
So this new recipe worked incredibly well, achieving amazing results. But it also created this fascinating and pretty controversial side effect that has everyone in the AI field talking.
Researchers started noticing this really peculiar trend. As the models got better and better at solving problems correctly, the step-by-step explanations they generated, what we call their chain of thought, just started getting longer and longer and longer. It was like the model was learning it had to think harder to get the right answer.
And this immediately sparked a huge debate. The optimists look at this and say, this is incredible. The AI is genuinely learning to break down complex problems and think more deeply. But then you have the skeptics and they're saying, whoa, hold on. This isn't better reasoning. It's just a weird flaw in the algorithm that happens to reward unnecessarily long and verbose answers.
And that leaves us with a really critical question for the future of AI. Is this longer, more complex thought process a feature we should be celebrating, or is it just a bug we're mistaking for a feature? What is the true price of machine reasoning in terms of cost, energy, and complexity? And what are we as a field willing to pay for it?